My dear students, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. And I'm happy to share with you all that today is our 71st International Physics webinar. So good evening to all here in Bangladesh, and a very good morning to all those who are watching this program live from USA. Hope you are well and safe from Corona pandemic. We're trying our best to adjust with this new normal situation. We can't continue our normal academic program inside the campus, so we have to start our online program to continue our academic program. Our Department of Physics, Pabna Science and Technology, has already started its online program, including online classes and online international physics webinars. And we have already completed our 70th international physics webinar. Today is a very important day for our department. Today I'd like to welcome you all to a joint session between Department of Physics, Pabna University of Science and Technology, and the Department of Physics Graduate Faculty of Material Science and Engineering, Arizona State University, USA in Material Science. And we have with us here today Dr. Arunima Singh, Madam, Assistant Professor, Department of Physics, Graduate Faculty of Material Science and Engineering, Arizona State University, USA, connecting with us from USA. And she has already connected with us, so I'd like to welcome her in our International Physics webinar. So good evening, Madam, and a very good morning to your part. And welcome to our International Physics webinar.
Thank you so much, Pretam. Thank you for the invitation, and I'm very excited to be giving a talk here.
It's a pleasure to host you.
Shall I start?
Yeah, I'll take a few minutes to introduce you. For those who are new, I'd like to inform that we have divided our webinar into three parts. First, we'd like to introduce our speaker with all of you. Maybe somebody well known to our speaker, but I'll try to introduce her to all of you. So I think you have already come to know the title of our today's International Physics webinar, and the title is the Material Discovery Enabled by Quantum Mechanical Simulation. And our speaker is Dr. Arunima Singh, Assistant Professor, Department of Physics, Graduate Faculty of Material Science and Engineering, Arizona State University, USA. So Dr. Arunima Singh joined the Department of Physics at Arizona State University as an assistant professor in August 2018. Prior to joining the ASU faculty, she was a postdoctoral associate at the Lawrence Berkeley National Laboratory in the Material Project team from 2007 to 2018, and at the National Institute of Standard and Technology in the Material Science Genome team from 2014 to 2016. She received her doctoral in 2014 from Cornell University and her bachelor in 2009 from Indian Institute of Technology, Kharagpur. We can see her research area. She worked in renewable energy, nanoscience and materials physics, computational modeling, nanotechnology, surface science. And we can see her Google Scholar ID, and her citation number is 1818. So thanks all for all of your patience. Now it's time to go to our speaker. So I'd like to welcome you again, Madam. You can start your session. It's your time.
Thank you again, Pretam. This was a lovely introduction. I appreciate it. I'm very excited to give this talk here. And today I'm going to be talking about how we can do materials discovery using quantum mechanical simulations. My talk today is going to be about two different projects. The first one is going to be about how we can discover new two-dimensional materials and identify their properties for practical applications in several fields. And the second one is going to be how we can use quantum mechanical simulations and combine them with data-driven science to identify new photocatalysts. And before I begin, I want to, I'm sorry, let me, not sure. Okay, there. So as you all know, ours is a materials-enabled society. The biggest advances in our society have been correlated with our discoveries in materials. For instance, in communication or transportation, where we have been able to develop transportation which would be suitable for space transportation, or transportation in sea, or transportation on land. You need different kinds of materials for all of these three environments. And similarly, all other advances in infrastructure, healthcare, power generation have been correlated with our understanding of materials and ability to engineer their properties. If you look at how materials are discovered, you can think about the Edisonian style. And this is an excellent example where if you see how Thomas Edison actually discovered filament materials for light bulbs, you'll find that he actually tried 6,000, more than 6,000 materials and candidates before he found a suitable material. And turns out that it wasn't tungsten. He found a carbonized filament material. So you can see that how much effort is required in discovering a new material. You have to try many sorts of materials for a particular application. And what if we were able to accelerate this whole process? What if we were able to say that we don't have to do these expensive experiments? Instead, we could perhaps use simulations to identify suitable materials, their properties, their structures. And what Edison found was carbonized bamboo, like I said. He wasn't even able to find tungsten, which was discovered much later. If you look at the traditional materials discovery timeline, it takes almost 18 years since a new materials is discovered to its commercialization. You can see there are several types of materials which have been discovered at various points in the history, and it took almost 20 years for them to go to a commercial stage. Is there something we can do to actually minimize this time? In the US, the Materials Genome Initiative was launched a couple of years back, where the goal was to be able to accelerate this materials discovery to commercialization process by combining computations, theory, and overall enable that. And one of the techniques has been using a computational materials discovery. So if you look at on the left-hand side figure, you have the typical Edisonian approach where you take materials of different types. You go to the laboratory, you do various tests on them, and you see if they work or not. If they don't, you throw them in the bin. And there might be certain materials which will work, and that is your star candidate. And that's a traditional Edisonian approach. The new approach, which has been pioneered by several leaders in this field, is taking all of your candidate material structures and putting them through computations. You're not explicitly doing experiments, but what you're doing is that you are feeding them through computations which are cheaper than experiments, they're faster than experiments, and oftentimes accurate enough to let you know what candidates are not going to work. You discard them and you check out the candidates which are promising, and you can do follow-up experiments. It's possible that this approach will accelerate the discovery of materials for certain applications. And the step of computations requires supercomputers, which are several hundreds and thousands and millions of hours of supercomputing time. And one of the most successful methods for doing this computation plus experimental approach has been solving the Schrodinger equation using the density functional theory. So what is that? The so-called density functional theory is an ab initio simulation technique where you solve the Schrodinger equation by using the density functional theory. And this density functional theory is a standard model for understanding the ground state properties. The total energy is taken as a function of the charge density. And the cone-sham formulation, as you see on the right, maps the interacting many electron problem to non-interacting electrons moving in a self-consistent field. It's a beautiful theory, and in principle, it's exact, but unfortunately, the form of the exchange correlation function is unknown. So there are several approximations for the exchange correlation function, and there are several density function theory codes one can employ. And these are typically run on supercomputers such as the Stampede supercomputer, which is available through NSF Exceed, or the Edison supercomputer, which is available through Department of Energy's NERSC supercomputing source. As you can see, there are several thousand cores at Stampede, and there are several thousand codes at Edison. So not all of them are used at a time, But this is the scale of supercomputing which is required to do these simulations. And using this computational method, one can say that we probably have a virtual lab for material science and engineering. You're able to discover the structure of materials. You're able to characterize their properties. You're able to look at perhaps their electronic structure. And you're able to find potential applications for these materials. And in fact, I myself have done several studies where we have discovered the structure of more than 20 two-dimensional materials, which were never synthesized before, looked at their properties and was able to suggest applications for them. The properties which are computed from DFT, as you know, it's a ground state theory, range from looking at the phase stability, the phonon spectrum, and the defect distribution in materials, the band structures, or the charge densities. And in fact, there are many, many other properties which can be computed from density functional theory. I wouldn't go into the details, but I want to mention that there are some which can be predicted with reasonable accuracy, perhaps 5%, within 5% of the experimental measured, while others are much more inaccurate, and there are higher order methods which can be employed. But what's great about these simulations is that they're transferable to large scale simulations. And if you're looking at time dependent properties, then you can perhaps use the properties computed from density functional theory and then use them to do molecular dynamic simulations. I want to mention the materials project effort, which has led to one of the most well-known databases of materials. And in fact, the director of the materials project has at some point said that it's almost a Google for materials, not really as big as Google database, but it is quite monolithic. There are about 130,000 materials in the materials project database. And you can go to this database, and if you're interested in a certain compound, for example, say TiO2, you can find that specific phase, and you will find several computed properties of that material, including its structure, lattice parameters, band structure, or even its stability in aqueous media. And the materials project is a multi-institution effort and multi-PI effort. And at some point, I was also affiliated to this. And the page you're looking at right now is some of the work I have done with the team. It is a wonderful collaboration of looking at materials, their properties, and identifying new applications and new materials in different classes. What I'm doing in my current group at Arizona State University is looking at the properties of the surfaces of materials, and in some sense, going from the materials genome to the surface genome. I have looked at several studies myself where we have found that the surfaces play a very important role in real-life technological applications, and there aren't any coherent and systematic databases of surface properties. And in my group, we are looking at the surface properties of materials, the properties of adsorbents on materials, and heterostructures. And we're building a database where we have, in some sense, the surface properties, which I also like to call the surface genome. So that's what my group is doing currently. And today, I want to talk to you about a specific project where the surfaces play a very important role, and that is of photocatalysis. And I would talk about the high throughput screening for photocatalysis. Okay, so what is photocatalysis? Specifically, photocatalytic energy conversion processes. What are these? If you have water, you could convert it to hydrogen and oxygen gas. And as we all know, we have a lot of water on Earth. It's going to be a wonderful source of energy if we could convert water to hydrogen gas. It would be a clean, renewable form of energy which is environmental friendly. However, as we all know, a glass of water doesn't spontaneously convert to hydrogen and oxygen. We have to supply some energy to it. It turns out that energy is 1.23 electron volts. So even though this is not a spontaneous reaction, if you use solar energy of sufficient, solar light of sufficient energy, and use a photocatalyst, which has suitable band gaps and band edges, you can generate electron-hole pairs where the electrons and the holes will catalyze redox reactions for this conversion. What you require is the band gap of your material should be larger than 1.23 volts, and its band edges should straddle the potentials for the redox reactions of water splitting. So that's an intrinsic property of a photocatalytic material. If I was able to find materials which satisfy this condition along with others, then I might be able to use sunlight to convert water to hydrogen gas and oxygen gas. This is a very powerful idea, and this has been thought of for several decades. And in fact, there are several other chemical energy conversion, which can be done. For example, converting CO2, which is a greenhouse gas, to perhaps an alcohol or alkanes. And here what we're doing is you're converting a pollutant to a usable fuel or a chemical feedstock. And again, you can use sunlight and a suitable photocatalyst to do that. In a similar manner, you can convert nitrogen to NH3. So there's a huge promise of converting sunlight, using sunlight to convert chemicals to fuels. What we need is suitable photocatalysts. And I'm going to talk specifically about the CO2 reduction reaction, where you convert this greenhouse CO2 into usable fuels. Here in the figure at the bottom, you're looking at sunlight, which shines on a photocatalyst. And if the sunlight has sufficient energy, the photocatalyst is going to generate an electron. And if you put CO2 gas in the system, bubbled along with some water which has protons, then you can facilitate these reactions where you form an alcohol, an aldehyde, formate, CH4 and C2H4, and many other products. And you'll notice these products have similar energies of formation. Now, what's challenging is that you only want one product from this reaction. But since all of these reactions have similar energies, you form multiple products. And that's a big challenge right now. The photocatalysts for CO2 reduction known to us have poor efficiencies and product selectivities, which is evident in this figure here, which I've taken from this experimental article. You look at the Faradic efficiency. You can see it's less than 2%. And you can also see there's several products which are formed when you use MOS2 as a catalyst for CO2 reduction. And if you look at the number of photocathodes which are known to us, there are many kinds of photocathodes which experimentalists have investigated so far, including bulk materials, some certain nanoparticle phases, and mesoporous phases. And all of these have this limitation that the efficiencies are quite low, and the product selectivity is quite low. The goal of my work, which I'm going to present in the next few slides, is to identify new materials which have never been considered by experimentalists using computations. So let's see, how can we do that? What sort of information do we need to start? And what sort of information can we get in the end? Okay, so the first question I ask is, what makes a good photocatalyst? What are the properties of a good photocatalyst? And here I'm listing some 9 properties, and we'll go through them slowly one by one. But let me categorize them into 2 different categories. The first one are the first 4, which are absolutely required. If you do not have that property in your photocatalyst, there is no chance that you could have CO2 reduction. And the rest of them are desirable properties, which would make an efficient photocatalyst or a selective photocatalyst. So the first four include thermodynamic stability of the material. Your material should be stable. It should have sufficient band gap so that it can absorb a good fraction of the solar spectrum. It should be corrosion resistant. So if you place it into water, it should not corrode away. And its band alignment, it should have band alignment with the reduction potentials of CO2. The desirable properties include that the competing reaction of hydrogen evolution should be suppressed. Your protons should actually react with CO2 or its intermediates instead of reacting with self and forming hydrogen. These materials should have small exciton binding energies so that you have lower overpotentials. And they should have low exciton recombination rate so that you don't lose energy because of this recombination. It should be, of course, cost efficient, environmental friendly. So I have a huge list of what I want. How do I get there? What can I do from simulations that I can identify these properties? So what I can do is I can look at the existing materials databases, such as the materials project or the Citrin database or the materials data facility. There are several databases which have come up in the last few decades, and they have been instrumental in doing these high throughput studies for discovery of materials of several classes. So we decided to work with the materials project database because it has all the materials which are reported in the inorganic crystal structure database. An inorganic crystal structure database is a database of experimentally synthesized materials, about 35,000 of them. And the materials project also has additional structures which have been predicted using data mining and chemical substitution. What we did was we looked at this materials project database, and it had about 70,000 inorganic compounds at the time the study was done. And we thought, let's look at these 70,000 compounds and see if we can identify materials which will match the conditions for good photocatalysts. What we did was a successive screening for the properties to minimize the number of computations which we had to do. And the first property we looked at was the thermodynamic stability. The materials project database has the energy above hull, which is the energy with respect to the most stable solids at that composition for the materials. And since the materials project has this computed already, what we needed to do was identify a cutoff for that energy, which is a measure of the thermodynamic stability, and pass the candidates, 70,000 candidates, through this first screen of ours. We selected a criteria of 80 millielectron volts because that corresponds to about synthesis temperatures of about 1,000 Kelvin. The second criteria which we chose was looking at the band gaps of the material, and the materials project has the band gaps computed using PB and PB plus U functional. And as I mentioned earlier, even though the density functional theory simulations are in principle exact, the functionals have an approximation to them, which makes their band gaps inaccurate by about 30% or so in most cases. So we selected a range which was representative of that underestimation in band gap, but still could give an idea of materials which would be in the visible part of the solar spectrum, which constitutes for a major fraction of the solar energy. We found about 11,000 materials. And these two properties were already there in the materials project database. So the materials project database was monumental in shortening down the list from 70,000 to 11,000. The next bit was looking at how stable are these materials in water. Looking at the stability is critical. These reactions happen at reducing conditions, and reducing conditions can be highly corrosive for materials. Most materials hydrolyze or convert to their metallic forms under these conditions. But there was no way to assess the aqueous stability of metastable materials using the existing routines in the materials project. And then we decided to look at the band edges, which is the band alignment with CO2 reduction potential, and certain other more accurate but slightly more expensive functionals to compute the band. Now we can't do this steps 4 and 5 unless we know something about the step 3. So what we did was we looked into how can we assess the aqueous stability. What can we do to identify that? If you look at the methods out there to assess the reaction or the performance of materials, solids, which are in contact with aqueous media, I plot them here on this slide with the ones on the left-hand side being highly accurate but highly expensive, and ones on the right-hand side being quite inexpensive and fast, but their accuracy is compromised. So at the very left, we have very accurate quantum mechanical simulations where we do explicit calculation for the solvent molecules, such as the water molecules shown here, and your system in consideration, and you relax the ionic and electron degrees of freedom. This is very, very expensive because the configurational entropy of your solvent molecules is enormous, and it's not possible to capture that. Furthermore, you can't really look at the effects of pH and applied potential in this approach, especially for 11,000 materials, which we had for our system. The other approach is you can look at a hybrid quantum mechanical and continuum system where you use a continuum model for your electrolyte or solvent, and you use first principles for your material. Even though this is much cheaper than the quantum mechanical method, you still have to use ab initio simulations for your solid in consideration, which makes this process expensive. And again, you cannot look into the effect of pH. What we decided to do was we decided to go with identifying a method which would be based on a phenomenological model where you're going to use DFT computed energies and use that to make these electrochemical stability maps, which I'll describe in a bit, which can tell you about the stability of metastable materials as a function of potential and pH. Okay. So what is this phenomenological model, and how does it help in assessing the aqueous stability of materials? Before we go there, let's go very simple. Let's just go and look at what happens if I place something in water. Let's assume that something is iron. So if you put iron in water, you're going to get these are some of the possible reactions which could happen. You put iron in water, it could form a hydroxide. It could form an oxide, or it could just form these aqueous Fe2 plus species and corrode. And which one of these reactions is actually stable? You can determine that using the Nernst equation, which gives you the relation between the chemical and the electrical driving force. And if you know the reaction energies of each one of these reactions, and you knew what pH you're at, which is basically the concentration of hydrogen ions, and the potential you're at, you can generate these so-called Pourbaix diagrams, which give you the stability region of different species as a function of pH and potential, which are possible for a specific system when it's placed in water. So this is the Pourbaix diagram of iron when it's placed in water. So iron, oxygen, and hydrogen. Those are the species which you're going to see on this diagram. If you look at this yellow region here, where below -1 volts at any pH, iron is stable. But if you go at slightly higher potentials, such as 3 electron volts or 4 electron volts, iron, when placed in water, actually forms this oxide ion, and the iron film just dissolves in an aqueous form. But in this another region, this yellow region here, the reaction of iron to form FeO3 is the most stable step. And this Fe2O3 could form on the surface of iron, and it could potentially form as a barrier for further reaction of the water with the iron. Or it could be porous, and then it could still allow the reaction of iron continually and changing the whole iron to iron oxide. So it could potentially be a passivating film. What these Pourbaix diagrams have actually been experimentally determined by Pourbaix himself, and there are about the Pope diagrams for 85 elements are available in the literature. But it's very difficult to get the experimental energies for multi-element solids. All you need to do make these Pope diagrams is know what are your redox species, what are the redox reactions, and what are the energies of those redox reactions. If you know that, you can make these Pope diagrams. Now, to know what the reaction energies are for multi-element solid, it's quite tricky. The number of redox species in a ternary or a quaternary system becomes prohibitively large. You can see the axis on the y-axis is in logarithmic scale. And in that case, what you can do is you can combine DFT-computed solid energies with experimental energies for aqueous species, and then you can generate Pope diagrams for systems which are binary, ternary, up to essentially infinite number of elements in them. And this has been done by Pearson et al. And this formalism, they have shown that you can generate these Pope diagrams for, say, systems like iron, vanadium. And you can see that the Pope diagram for iron and vanadium is much more complex than the Pope diagram of iron, oxygen, and hydrogen system. You can see there are several phases which exist, including several oxides of vanadium, iron, and several ionic species of iron and vanadium. What I did was that I was able to develop an instability criteria, which is denoted by the energy with respect to Pope stable phase of a particular compound with respect to the Pope diagram of it. So what you're looking here is the electrochemical stability map of a metastable compound FeVO4. And metastable compounds by design cannot be on the Pope diagrams. The Pope diagrams only look at equilibrium compounds. What we did was we looked at, we generated this measure of delta G, that is the Gibbs free energy with respect to Pope stable phases for compounds, and show them as a color bar. So what this color bar shows is that in this bluish region, FeVO4 is expected to be moderately unstable with respect to Pope stable phases, but in these yellow regions, FeVO4 is very, very unstable, and it is expected to dissociate to the Pope stable phases. We have this measure of the Gibbs free energy with respect to Pope stable phases, and we thought that perhaps it could give a quantitative estimate for how unstable or stable is a material at a particular pH and a particular potential. So we did validations against what information we had in the literature and experiments which were done by our collaborators at Cal. For the validation against the information which we had in literature, what we did was we plotted the Gibbs free energy of all of these materials for which we had data about their stability, aqueous stability in a direct or an indirect form in the literature. And at the pH values where the experiments were done, we calculated the Gibbs free energy at 1.5 volts versus RHE. And that was the potential at which the experiments were done in all of these cases. What we found was, and surprisingly enough, we found there was a clear correlation between the delta G value and the stability of these materials from the literature. So the materials which had delta G values of less than 0.5 electron volts per atom were reported to be stable. And the materials which were above that value, up to about 1.2 electron volts per atom, were reported to form passivation films, which would be a few nanometers thick, and that would prevent further corrosion. Materials which had very high delta G values were reported to corrode. And it's surprising that these delta G values of up to 0.5 EV per atom, even though your materials are unstable by that amount, they were still not dissociating to pore-based stable phases, and we think that it's perhaps because the energy barrier for the solid to solid decomposition, which was the case in all of these systems, as you can see, the pore-based stable phases are all solids. This is denoted by black circles over here. That was perhaps quite high. And also in the experiments, there might be concentration and temperature fluctuations, and we had assumed a fixed concentration and a temperature of 300 Kelvin. And for the phases which were reported to passivate, we found that our predictions of what the pore-based stable phases or the decomposed species would be, that matched with what was reported in the experiments. For instance, for FeVO4, those reports that there's perhaps iron oxides on the surface. So we found a very strong validation of our work by looking at the literature, but of course the literature is not, we don't always have single crystalline materials. Sometimes they're porous, and oftentimes the surface characterization hasn't been done, and our comparison was more indirect. So we went to our experimental collaborators who were able to grow FeVO4, which is a metastable material, in their lab, and they were able to do experiments including XRD, XRF, and XPS to show that there's corrosion where it's expected and there's passivation where it's expected, and the passivation film composition is in excellent agreement with what we predict from our theory. So by this bifold validation, we were able to show that our formalism of looking at electrochemical stability maps gave a quantitative estimate for determining aqueous stability. And we found an excellent agreement in the DFT predicted and experimentally observed electrochemical behavior. And this is a very powerful technique. We actually made this technique available on the Materials Project website, not only through the website, but also through their code base. So what you can do now is go to the Materials Project website, enter a compound of interest, for example, TiO2, which I've selected here, and you can find many of its computed properties. And if you scroll down, you go to the generate phase diagram, you click on aqueous stability. Within a few seconds, the electrochemical stability map of TiO2 is generated. As you can see, now you can look at whether TiO2 is going to be stable at a particular pH or potential, and you can see if it's not, then what are the pore-based stable phases. You can change the concentrations, and now just by a few clicks, you can understand whether a material is going to be stable or not. So what you see here is, as the Materials Project Director likes to say, is just the tip of the iceberg. There's a lot of work went behind this, where we had to do a code development and multiple from multiple angles, and this code has also been made available. So now you can go ahead and you can data mine for durable, corrosion-resistant photocatalysts. Not just that, you can also find materials for other water-based applications. And if you're interested in this, I would highly encourage you to go check out our code on the Materials Project website. All right, so let's come back to CO2 reduction photocatalyst. And we were stuck at this point where we did not know how to determine the aqueous stability. This aqueous stability, now that we have a quantitative measure because of electrochemical stability maps, we looked at the delta G with respect to pore-based stable phases, and we set it to 0.2 eV per atom at the reduction potentials where CO2 reduction happens. And we found that there were only 500 materials amongst the 11,000 which satisfied this. This really highlights the importance of looking at the aqueous stability. And then we did more accurate calculations of the band gap, and we found about 163 were in the range of visible light spectrum. And we also chose a slightly higher value than the 3 eV range, which is in the visible light spectrums, to account for the changes in band gaps due to surface states or perhaps defects in the system, which we haven't really exclusively considered in this work. And then we looked at the bandages. It should be enough for the CO2 reduction potentials. And we found there are 52 materials which emerged out of this screening. So from 70,000 materials, we were able to get to 52 materials which had these properties which are absolutely required to be a good CO2 photocatalyst. Out of these 52 materials, the 43, only 9 had been previously studied by experimentalists, and 43 were new candidates which had never been considered for CO2 reduction before. Okay, so I've done this screening based on computations, and I've already mentioned that these computations could be inaccurate in some cases. So why should we believe these results? Why should we say that these 52 materials are actually going to be good for CO2 reduction? What if I change the screening criteria by a little bit here and there? What would that do? Is this work really reliable? I had this question just like you do. And what we did was that we did a validation against known photocathodes for the screening. And we took all the photocathodes which were known to us at the time we did this study. And you might recall this list from the first few slides, where we have all the bulk photocathodes, the nanoparticles, and the mesoporous photocathodes listed over here. And we fed it into the screening funnel which we have designed to see what emerges out of it. Do we get any of these candidates out of it? And if we do, what is their specific strength? For all of these candidates, except one, which was not in the inorganic crystal structure database, we were able to find about 532 phases. Note that it's not often that in the experiments that they note what would be the phase type, what is the crystal structure of the material, and of course we had nanoparticles. So we just decided to include all the phases for these 44 compositions. And we were able to find thermodynamically stable phases for all of these 44 compositions, so about 200 of them. And when we look at the band gap, the number of materials which pass through reduced quite a bit. We are left with 27 phases, 27 materials with about 200 phases. And the materials which dropped out had a band gap less than 1 eV, more than 2.5 eV, and the ones which had band gap more than 2.5 eV are known wide band gap materials, oxides, and the ones which are less than 1 eV, many of them are known low band gap materials. And then we look at the aqueous stability. You can see the largest fraction of materials were actually dropped here. There were only 30 phases out of the 202 phases which were expected to satisfy our aqueous stability criteria. Many materials which were deemed unstable by our screening criteria, and in fact, in experiments, there is evidence that many of these materials have been are unstable. However, unfortunately, the surface characteristics and their stability with aqueous media is not always reported. And then when we look at the band gaps with a more accurate functional, there's about 8 which remain. And the ones, some of the oxides, we get a band gap much higher than 3.5 eV. For certain other materials, we were not able to do the calculations because these calculations are fairly expensive and it did not complete in the wall time of the supercomputing sources. And then we look at the bandages and we find all of these 8 materials had suitable bandages for CO2 reduction, and what emerges out of this screening is fascinating. We see the most widely studied CO2 reduction materials emerge out of the screen: TiO2, Ceria, MoSe2, WSe2. What it tells us is that the materials which come out of these screening are highly robust in aqueous media and have a band gap in the visible light range. And the screening is highly selective of materials which can satisfy these two things. So that means, if anything, our screening was very selective and was able to get candidates which are going to be extremely robust in aqueous media and have the promise of absorbing a good fraction of the solar spectrum. So what are these materials? And it's shown here on this table, and I apologize, this is really small. However, my goal is not for you to read this table, but we just want to do a broad analysis of the materials which we find from the screening. And I would encourage you to look at the paper if you're interested in the details of these materials. What I want to highlight is that the materials which I just highlighted through these blue shaded regions are the only ones which have been reported in the literature as CO2 reduction photocatalysts. All of the others are candidates which have never been used for CO2 reduction before. And these are mostly oxide materials, the ones at the top. And you can see there's a few selenides and a telluride which has been studied before. What you would find interesting is that out of these 43 materials which have never been tested for CO2 reduction, 34 of them actually have been synthesized for another application before. That means all of these materials are not hypothetical materials. There are actually 34 of them where the recipe for their synthesis is known. So you could actually go to your lab and perhaps synthesize them and test them for CO2 reduction. I want to draw your attention to their chemistry. There's many arsenides, there's several selenides, and surprisingly, there's many tellurides in the system which are rarely studied for CO2 reduction. So we've been able to identify different chemical classes for CO2 reduction, which are largely ignored for this application. And 12 of these materials are layered materials. So the advantage of layered material is that you can peel off individual layers from these layered materials, and these individual layers or bilayers or tri-layers enable us to tune their properties. So that brings me to the next idea of what would be the two-dimensional forms of these photocathodes. If I were to take these layered materials perhaps and form 2D forms of photocathodes, they would have an intrinsic advantage over the bulk material. I have the two-dimensional form on the left, and I have the bulk on the right. The two-dimensional forms actually maximize the surface area per amount of material. So I have more exposed spaces per amount of phases per amount of material in comparison to the bulk for a 2D form. So that means I have more reactive surfaces. And also, if a photogenerated electron and hole need to reach the surface, they have to travel much less if they're in 2D form, as opposed to bulk, where they have to navigate through grain boundaries, defects, before reaching the surface, which can lead to their recombination and loss of energy through that process. So these two intrinsic advantages make 2D materials particularly lucrative for photocatalysis and photocathodes, for our example, for instance. And in fact, indeed, there are many experimental studies which show that the incident photon conversion efficiencies for single layer or few layer materials can be orders of magnitude larger than for the bulk materials, as you can see, for tin oxide, tin disulfide, and zinc selenide. Pretam, how much time do we have?
We have about 12 minutes.
Okay, thank you. So, so intrinsic properties of nanoscale materials make them quite attractive for solar energy conversion. And we ask this question is, can we actually discover two-dimensional forms of the photocathodes which we have? And we had 3 different criteria for our study for the two-dimensional forms. The 2D forms have fewer number of atoms, so we can do more calculations for them. So the first set of criteria were synthesizability. We looked at photocathodes and the bulk photocathodes, and we looked at all the possible two-dimensional structures we could have for these photocathodes. We do not know this. Unlike for the bulk photocathodes, we had a materials project database which told us what the structure was, what the energies was. But in our case, we had to look at certain prototype structures and map the bulk photocathodes to those structures. And here are some of the structures which we had considered for a small subset of the bulk photocathodes. And in this rich structural space, we were able to find materials which were thermodynamically stable. The two-dimensional materials which were thermodynamically stable need to have a formation energy within 0.2 eV per atom with respect to its bulk form, which has been ascertained by certain heuristic measures by a couple of studies in this literature. And then what we did was we looked at its phonon spectra to see if it's going to be dynamically stable. So if I take a two-dimensional material and I stretch out two of the atoms in its lattice, for example, and I keep stretching, there should be restoring forces to bring those atoms back in. And that can be seen in a phonon spectra. If there are no restoring forces, the phonon spectra is going to have imaginary modes. And we found several structures which we had considered to be dynamically stable. And then we looked at its suitability, which was given by the band gap and the bandages. And what we did was, additionally, which we hadn't done for bulk materials and we could do for 2D forms, was look at their exciton binding energies and look at the adsorption energy of reaction intermediates. These two things are very complicated to simulate. For example, looking at the adsorption energy of reaction intermediates requires considering several intermediates and considering the different sites these intermediates could be on the surface. So we have to do a sampling of a huge surface. However, Stephen Torresi, who is a graduate student at Harvard right now, did these calculations, and he found that many of the 2D structures which we had studied were suitable for converting CO2 to CO. And what we had, and let me go back to the previous slide and summarize here. So what we did was we formed 2D forms of the bulk photocathodes, and we have shown its potential to be good CO2 reduction photocatalysts. Our intuition is that these 2D forms are going to be perhaps more more experimentally efficient and selective for the reaction. So the study is now published in NPJ 2D Materials and Application, and I invite you to take a look at it if you're interested. Now, both of these studies which I have shown here are just computational studies. There's no experiment validation, and this could be one of those studies where it's just a computational work which does not take into account the complexities of experiments. But I want to show you that we have actually done joint experimental and computational studies where we have done screening for photocatalysts using computations, and then our experimental collaborators were able to do experiments and verify that some of those candidates which we had screened for were actually suitable for CO2 reduction. I'm sorry, for water splitting. That's the one which we have done it for water splitting more than for CO2 reduction. So here on the right, we're looking at a study which was done using our collaborators at Caltech, where we had started from several phases of manganese-based ternary oxides, and we were able to do screening for materials using simulations and present 27 candidates to them. And they were able to do growth of these candidates, characterize their structure using XRD, and then they were able to do all of these studies in a high throughput manner, and they were able to look at their UV vis, look at their band gaps using UV vis spectroscopy, and then they use these scanning droplet cells to do a high throughput study of whether these candidates were actually converting water to hydrogen gas and oxygen gas. And indeed, we found these 5 new candidates which have never been studied for water splitting. And there are many other such success stories which I'm not going to be talking about today. But you can see that computations can play an enormous role in identifying new materials or materials for a specific application. All right, so I have only a few minutes left, and I'm going to talk about the discovery of 2D materials, their structure and properties quite briefly, depending on how the time permits. And I would like to focus on the basics of two-dimensional materials, though, and I apologize ahead, I might rush through the results. So what are two-dimensional materials? 2D materials can be defined as materials which are infinite in two directions, but finite in the third direction. And that means two-dimensional materials can consist of more than one sublayers. For example, graphene is a single atom thick honeycomb lattice of carbon atoms. And boron nitride is again a honeycomb lattice, which is single atom thick, consisting of boron and nitrogen in this honeycomb lattice. But MOS2, which has three sublayers, molybdenum in the middle, and then you have sulfur layers above and below that. And tin selenide has 4 sublayers, gallium selenide has 6, and so on. Now, when do you say that it's not a 2D material anymore? If the thickness of your two-dimensional film is such that its property approaches that of the bulk, then it's not considered a two-dimensional material. And these two-dimensional materials, now there have been predictions of about 6,000 materials using theory and predictive simulations, and their properties, including their band gaps, their mechanical properties, have a very wide range. They range from metals to insulators, from highly flexible to very rigid two-dimensional materials, and very reactive to very inert materials. And they find applications as piezoelectrics, photocatalyst, and nanoelectronics, and so on. So how were these two-dimensional materials actually discovered using computations? The first 2D material which was experimentally extracted was graphene. That was in 2005. And the structure of graphene is a honeycomb lattice with carbon atoms in it. What researchers realized is that perhaps we could substitute these carbon atoms to other elements and see if that would be stable. And that's how boron nitride was first studied, by doing elemental substitution in this structure. And silicene was the next one, and in silicene, the honeycomb lattice doesn't remain flat. The alternating silicon atoms are offset in the z direction. So one is at the top and is the bottom, and you have 2 sublayers. This led to discovery of many 2D materials, but the other approach was looking at individual layers of van der Waals bonded. How was graphene actually discovered? If you look at a pencil and if you use a Scotch tape to peel off the graphite from your pencil, and if you keep doing that repeatedly with the Scotch tape, you're going to get a graphene flake at some point. And what is happening is, as you do that every time, these individual layers of graphene are breaking. The van der Waals bond, which is very weak, is breaking, and the covalent bond, which is 10 times more strong than the van der Waals bond, remains. So your graphene sheet remains intact. And using that idea, people thought if you look at other van der Waals bonded bulk materials, we can find out other 2D forms which could be stable, such as MOS2, tin sulfide. And these are some of the materials which I had predicted using theory, and many of them were through looking at van der Waals bonded bulk. And using these techniques, people have discovered almost 6,000 two-dimensional materials so far. But there's the way to do that is, and I know we're short on time, so I'm going to perhaps end with this slide. And I'm not really going to get into the work which we had done, but I want to tell you that using ab initio simulations, you can determine its energetic stability and dynamical stability. So the energetic stability is computed the ground state energies and try to minimize its formation energy. You can then look at the dynamical stability, where you're calculating your phonon spectra, and you should not have any imaginary phonon modes, as I mentioned earlier. So using these two criteria, one can say, oh yeah, this 2D material is going to be stable. And here, even though the 2H and 1T prime structures have low formation energies for MOS2, only the 2H has stable phonon modes. The 1T structure has imaginary phonon modes, and thus the structure is not. That's how we determine MOS2. It's going to be stable in this 2H. I'm going to briefly mention that we did this study where we had to use genetic algorithm searches to identify structures which were non-intuitive, because we could not get them from elemental substitution or by looking at van der Waals bond in bulk, because there didn't exist any. So with that, I'm going to just go to the end of my talk. Let me just in the interest of time, I'm going to go to the end of my talk, and I want to thank all my collaborators, the various institutions I have been affiliated with, all my collaborators at the various institutions I work with. But I want to thank Christine, my postdoc advisor, Francesca, my postdoc advisor, and Professor Henning, my PhD advisor. With that, I end my talk here, and I want to thank you for your attention, and I'm going to take any questions.
Thank you, madam, for your wonderful and nice presentation. And I think the students have learned a lot of things in material science. So we have got some question in inbox and comments. So if you allow, we can start reading the question.
Yeah.
So we have some question in inbox. So what is nanoribbons?
So nanoribbons, if you look at a two-dimensional sheet, here you're looking at a hexagonal shape of two-dimensional material. But instead of having an hexagonal shape, if you had these two edges, which are, I hope you can see my mouse, if these two edges were infinitely extended on the top, and these two edges infinitely extended on the bottom, then that would be a nanoribbon.
So another question in the comments. So according to material science analysis, so what is the relation between nanocomputing and quantum computing?
So I suppose you're asking about the computing which we did in this work and quantum computing. Is that what the question is?
So according to material science analysis, what is the relation between nanocomputing and quantum computing?
Okay.
The relation.
It's an interesting question. Thank you. I wouldn't say that this computing is really nanocomputing. I would say more that it is quantum mechanical simulations, and that is fundamentally different from quantum computing. And in quantum mechanical simulations, you are starting off with the position of atoms, a guess for where the position of atoms will be, and how many valence electrons you have on those atoms. And then whether you have a periodic system, or you have an isolated system, you solve for the Kohn-Sham equations, which help us ascertain what would be ground state charge density. And then from there, you can calculate all the properties of the materials. On the other hand, quantum computing is related to computing done by qubits, and there the kind of calculations which you do are much more primitive. You can do basic calculations such as addition of numbers, subtraction of numbers, but that is fairly fast in comparison to quantum mechanical simulations. These are actually both fundamentally different classes of simulations.
So thank you, madam, for accepting our invitation, and thank you for nice presentation and wonderful discussion session, madam. So hopefully in near future we'll arrange another webinar with you, and we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology. We are very grateful to you, and I think our students have learned a lot of things about material science and this technology. So thanks again.
Thank you so much, Pretam. This was a pleasure, and looking forward to seeing you again. Thanks.
Thank you. Bye for today. Good night.
Bye. Bye.